Hi, so this is section 4.4, which talks about the Cauchy-Gaussat theorem, which is very important and implied by the Cauchy-Riemann equations. The Cauchy-Riemann equations, if I remember correctly, are they're the meat in our sandwich, our complex variable sandwich, and everything else you've seen so far is a reflection of those properties that the Cauchy-Riemann equations encode. They're phenomenally important, and the Cauchy-Gaussat theorem is phenomenally important. So I'm going to begin this section with a little lemma. Let f, complex numbers be analytic on some open region. Not a domain, just some open region, R in C. Then the integral gamma fz dz is path independent if and only if, or path independent for every contour gamma in R, if and only if fc z dz equals 0 for all closed contours C in R. Proof is pretty reasonable. So that gamma 1 and gamma 2 be contours in R not equal to each other, gamma 1 not equal to gamma 2, with the same start and end points. Then gamma 1 union minus gamma 2 is a closed contour. And as the integral over gamma 1 union minus gamma 2 f of z dz is equal to 0 if and only if the integral of gamma 1 of f of z dz equals the integral of gamma 2 f of z dz, the result follows. Which is great. It's pretty simple. This asks us the question, when are closed contours, when is the integral of a function of a closed contour equal to 0? Because that will tell us that it's path independent, and of course that will tell us when we have an antiderivative by the chain of results we've seen so far. And that brings us to the Cauchy-Gaussat theorem. Which is theorem 4.4.2 in the notes. If f is analytic at all points within and on a closed contour gamma, then the integral over gamma of f of z dz equals 0, which is extremely useful, and you should remember it when you want to apply it to results, because it simplifies what would otherwise be a lot of work. Okay, so the proof of this is actually very difficult and complicated, but it is easy if we assume that f is differentiable. So this is sometimes called Cauchy's theorem. full proof of the Cauchy-Gaussat theorem relies on the same ideas as Cauchy's theorem, but of course, because we don't have continuity of the derivative, it's a little more awkward to prove. And when I say a little more awkward, I mean quite a lot more awkward. But anyway, so the proof of the weaker version. So let R be the region closed by gamma. Let f of z equal u of z plus I v of z, the real and imaginary parts of f. Green's theorem Green's theorem implies two statements. The integral over gamma of u dx minus v dy is equal to negative the double integral over r of del v del x plus del y del u del y dx dy. And that is suspicious. And we also have that the integral over gamma of v dx plus u dy equals the integral over r del u del x minus del v del y. And again, you should recognize these as the Cauchy-Riemann equations when they're set equal to 0. So, the integral over gamma fz dz is going to equal the integral over gamma of u d so small change in z will be a small change of x plus a small change in y. So multiply it all out, and this is u dx minus v dy plus I integral of gamma v dx plus u dy. Putting it all together implies the integral over gamma of f of z dz equals 0, and the full proof can be done in a similar fashion. So what's very important here is the Cauchy-Riemann equations actually imply this. So get some examples. Integral over gamma sine z exp z squared dz equals 0, because sine z e z squared is entire, and therefore analytic on and in gamma. So the result tells you that the integral is 0. Don't need any more information. The integral over gamma of 1 over z squared dz. Gamma is so the this thing here is only not analytic at 0. It's analytic everywhere else except at 0. 0 is not contained inside gamma. So the integral over gamma 1 over z squared dz equals 0. Boom. Look how easy it is to do integrals. again, it's going to equal 0 if, well, 0 is not inside gamma. So if we have some region that looks like this, with 0 inside, then we don't know what the integral will be, but we can work it out. We can choose a circle small enough, and we can join that circle up with a curve. So we have gamma, let's call it gamma 1, and gamma 2. We deform things very slightly. Gamma, I'm going to call it gamma epsilon because we're taking very small steps here. And I'm going to call this gamma 2 plus, gamma 2 minus, gamma 3. Then we know that on this whole portion on the inside here, of course, 1 over z is analytic. So since this portion in here is analytic, we know that this integral will be equal to 0. So this is the integral over the gamma bit, integral over the gamma plus 2 bit, integral over the gamma 2 minus bit, and integral over gamma 3. So this is like we can travel around. You have to pay attention to some signs in here, but essentially what this says is the Cauchy-Gaussat theorem tells us that the integral, and I won't write the function out, but the integral of gamma epsilon plus the integral of gamma epsilon 2 plus the integral of gamma 2 minus, that's a plus, is equal to the integral of gamma 3, negative gamma 3. 1 over z, 1 over z, 1 over z, z. But we know roughly what these integrals are going to look like. We worked out before what the integral over gamma 3 was as epsilon goes to 0. This thing here, if we think about the limit of these things, we know that, because we calculated it earlier on, the limit as epsilon goes to 0 of, we'll have a minus sign in here, and note we've got a direction change. So the integral of minus gamma 3 minus 2 pi I. And that's because we're going the other way around. We're going the other way around the circle in this particular case. It's my claim that the integrals for gamma 2 plus and gamma 1 minus are equal to each other, that they will eventually disappear. Now that should be pretty clear because the function that we're iterating over here, 1 over z, is continuous in this portion. So we can take limits of everything, and eventually in the limit, as epsilon goes to 0, gamma 1 will tend to the same as gamma 2. So in the limit as epsilon goes to 0, gamma 2 plus is going to equal minus the limit as epsilon goes to 0 of gamma 2 minus. And that will imply that the integral over gamma 2 plus of 1 over z dz will equal minus the integral of gamma 2 minus 1 over z dz. So in particular their sum will equal 0. And lastly, we have the limit as epsilon gamma epsilon 1 over z dz will equal the integral over gamma of 1 over z dz. So 0 equal to the limit as epsilon goes to 0 of the integral of gamma epsilon plus the integral of gamma 2 plus the integral of gamma 3 minus plus the integral of gamma 3 that's the integral over gamma 1 over z dz plus this is the integral over, well, the limit as epsilon goes to 0 of gamma 3 1 over z dz. And because we're going the other way around, this is going to end up being minus. I should probably put a plus in there just to make sure I've got everything right. So this implies that the integral over gamma 1 over z dz equals 2 pi I. And of course, gamma here was an arbitrary shape. This is not an exact proof. And the details for working through this, there's quite a lot of detail, a lot of checking that limits of things behave in the appropriate way and so on. But I hope it's clear that as gamma 2 and gamma 2 plus and gamma 2 minus, as the epsilons get closer, is reduced, so that these points get closer and closer to the axis, these lines get closer and closer to each other, and because they're going in opposite directions, the integral, the contributions that they make to the total integral will disappear. Similarly, the integral of the limit of the gamma epsilon is equal to gamma, and limits will respect that because we're dealing with everything as infinite portions for curves. So there are some theorems that help to describe exactly when deformations like this can happen, but for our particular case and for this particular course, you don't need to worry too much about it. You're not going to be confronted with the difficulties that could come up. When functions are nicely behaved, in particular they're continuous, this kind of stuff works. So in particular you can chop out where the zeros are with a little circle around them, and then it doesn't matter what size or shape neighborhood you're dealing with around them, you'll just pick up the contribution for where there's an issue, where it's not analytic. That's another way to interpret the Cauchy-Gaussat theorem, which is really that line integrals of complex functions over closed contours is all about where the function fails to be analytic, and the answer of the integral tells you something about that failure of analyticity, which of course tells you something about the Cauchy-Riemann equations and how far away the function might be from being hyperbolic or certain types of behavior with regards to that. So all of this is worked out in even more detail than I've given you here in example 4.4.5, and I suggest you go check it out because it's a good read and it's worth taking a look at. Right, and here we come to Cauchy's integral formula, which is really cool, and what the fundamental theorem of algebra relies on. If f is, so f is a function from the complex numbers, is analytic inside and on a simple closed contour, gamma, and if A is any point inside gamma, then the value of f at A is equal to 1 over 2 pi I times the integral over gamma of f of z minus A dz, where gamma is traversed once anti-clockwise. A few things to say. Because we're dividing by A in here, this will be non-zero, because even though f is analytic inside and on gamma, this function may not. I mean, it might still be, in which case the result will be 0, and if A will be equal to 0. But it's the division by z minus A in here that introduces the non-analytic behavior at a, where the integral will give the value of f of a, or 2 pi I times f of a. Another way to interpret this is, if you know the value of an analytic function on a closed and simple contour, then you know the value of that function anywhere inside that closed and anywhere inside that simple and closed contour, as long as you know the function is analytic in some sense. Analytic functions, another way to view this is that f of a is somehow the average of the values of the function z over the gamma weighted by 1 over z minus a, which is the, you can think of it as the vector that describes the distance from z, which is on a, z, which is on gamma from a. So this is the weighted average of the values of the functions, or value of the function on gamma, gives you f of a, well, after you adjust for factorization. Another very useful result that you should think about a great deal and be carefully cognizant of. Okay, so the proof's worthwhile seeing and working through, but it involves some estimates of the nature that I have avoided talking about so far. So it's a good idea. Just strap in and bear with us a little bit. Okay, so I'm going to rewrite f gamma f z minus f of z over z minus a dz, so that's the main integral here, is going to be equal to f, the integral over gamma of f of z minus f of a plus f of a over z minus a dz, and this is going to be equal to the integral over gamma of f of z minus f a over z minus a dz plus the integral of f of a over z minus a dz. So just to help you visualize what's going on here, we've got some region gamma, we have some point a. Because I know the function f is continuous, there exists some little ball, there's my gamma, around a, which is fully contained on the inside of gamma. So I'm going to call this gamma r. Gamma r is going to be equal to z0 to pi for z of t equal to a plus r eit. And for future reference, the derivative of this is going to be r-i-e-i-t, and the modulus of the derivative of this is r. Now, since f is analytic inside and on the interval, I know that it's analytic inside here, so I can perform the same technique that I used before. Here's my gamma. Gamma, let's call it r epsilon. Let's call this gamma epsilon plus, gamma epsilon minus. So, using the same technique as before, what I end up showing by taking the various limits of all these bits is that the integral of f z minus f a over z minus a dz gamma is equal to f gamma r, I've removed the epsilons after taking the limit, fz minus fa over z minus a dz. And I can estimate this now. I know that the modulus of the integral gamma z f of z minus f of a over z minus a dz is equal to the modulus of the integral from 0 to pi f z t minus f of a over zt minus a z dash t dt. That's less than or equal to the integral from 0 to pi of f z t minus f of a z t minus a z dash t dt. Now, since f is continuous on and in gamma, I know that there exists an m, so that for all z on and in gamma, f z t modulus minus f of a is less than m. And I also know that the modulus of z dash is equal to r, and the modulus of z of t minus a equals the modulus of r I t, which equals r. So the modulus of gamma r, the modulus of the integral over gamma r of f of z minus f of a divided by z minus a dz is less than or equal to m times the integral from 0 to 2 pi. Well, that's going to be r, and that's going to be r. So that's the integral dt, which equals m times 2 pi. Now it's worth thinking about this m just for a moment. What exactly is it? We know that the function is continuous. So we know that for all epsilon greater than 0, there exists a delta greater than 0, so that z minus a is less than delta, then the modulus of f of z minus f of a is less than epsilon. So can choose r less than delta, then m will be less than epsilon. So integral over gamma r f of z minus f of a over z minus a dz less than or equal to epsilon 2 pi. But epsilon was arbitrary. Epsilon is any number greater than 0. And so this implies that since the modulus is equal to 0, the integral itself, well, the complex number that the integral equals must equal 0. So that implies that so we now know that the integral over gamma of fz minus z minus a dz is equal to the integral over gamma r of fa z minus a dz. And it is now an exercise for you to use thinking about this r to show that this is equal to fa 2 pi I, which implies the result. This is an extremely useful theorem because it allows you to calculate the values of an analytic function inside a contour integral by calculating the contour integral, which is quite remarkable. A point z0 is a singularity. or singular point of a function f if f of z is analytic at some point in every neighborhood of z0, but is not analytic at z0. A singular point is isolated, or an isolated singularity if f of f, if f of z is analytic at every point in some neighborhood of z0, okay, so here's an example. Integrate gamma sine z over sine squared minus 1 dz minus 1. Gamma can be an oval, whatever, doesn't matter. So sine z sine squared minus 1 is analytic everywhere inside and on gamma except at plus or minus 1, where there are singularities because of the bit underneath. Using the same technique as before, we can deform gamma. So if we have we can alter this so that at 1 and as before, gamma epsilon and the various components that make this up. And in the limit, as epsilon goes to 0, this is going to be the contour, which is two bits of the contours that look like this, and I'm going to call this gamma minus 1 and gamma 1. So I can say that the integral over gamma of sine z over z squared minus 1 is equal to the integrals of gamma minus 1 sine z sine squared minus 1 dz plus the integral sine z minus 1 gamma 1 dz. And we can rewrite these to take advantage of the Cauchy's integral formula. I'm going to rewrite this as and gamma 1 will be rewritten as the other factor. Now since this component sine z over z minus 1 will be analytic everywhere inside and on gamma minus 1, we can evaluate this using Cauchy's integral formula. And similarly for this term, the result is after using standard properties of sine. Here's another example. And gamma is going to be the circular radius 3 based at z minus 2. So it's worth noting that minus 3 plus I plus 2 is equal to minus 1 plus I, and that's the square root of 2, which is less than 3. So 3 plus I is inside gamma, and that's going to be a problem here because this function will be analytic there, but by Cauchy's integral theorem this is going to be equal to z squared, z plus 3 minus I dz, and because z squared is itself analytic everywhere on and inside gamma, this is equal to 2 pi I times 3 plus I squared. Minus. And there's some other examples in the notes on page 101. Right, we have another theorem which will be very useful as well. Generalized Cauchy integral formula. If f is analytic on and inside a simple closed contour gamma, and if A is inside gamma, then for all positive integers, the value of the nth derivative of the function f at A is n factorial over 2 pi I times the integral over gamma of fz over z minus A to the n plus 1 dz, where gamma is traversed once anti-clockwise. So the important point about this is that integral can be performed regardless of how many times you'd like to differentiate it. So if f is analytic, so differentiable once, the integral on the right hand side will always make sense, and so the derivative will always exist. So analytic means differentiable once, and that means differentiable as many times as you like. And we knew that already because we know that if something's analytic, then its derivative is also necessarily analytic. But this is a different way to state it that gives an explicit formula for it. So the proof follows very similarly to the proof before as well, and there's certain bounds that are worth approximating. I'm going to suggest that you read through the proof yourself. It's given in the notes and is very clear. It relies on the following manipulation. Remember that the derivative of something is the limit. So we have fw minus fa over w minus a, and the limit of this as w goes to a will be the derivative for the n equals 1 case. We want to show that this is 2 pi I w minus a integral over gamma f of z 1 z minus w. Well, we know this is the case because that's two applications of Cauchy integral formula. Fw over w minus a is this term with this, and f a over wa is the second term. You can solve this and work out the answer and it'll look fine. This is the same as saying that we have 1 over 2 pi I what I'm saying with regards to this is rearrange and get the algebra out and see that this formula here comes from applying Cauchy's integral formula to each of the two terms that are given here. Right, so to show that this converges to that with n equals 1, so if you have a 2, the w should go to a, everything looks like it should work. You still need to prove that the limit of this thing on the right, as w goes to a, is well defined, and it's in the notes. It's worth chasing through because it will, hopefully following along, will help you understand some more epsilon delta stuff as well. Yeah, okay. So some examples. Integral z plus 1 over z to the 4 plus 4z cubed dz gamma. Gamma is going to be a circle traversed once in the anti-clockwise direction. So z4 plus 4z3 is equal to z3, z plus 4. So we don't need to worry about the minus 4 issue, but we do need to worry about the zeros. So there's an isolated singularity at z equals 0, which is inside gamma. So we rewrite the integral z plus 1, z4 plus z4 z cubed is equal to z plus 1 over z plus 4 over z cubed. And that looks like third derivatives. So we have f of z equals z plus 1 over z plus 4, and the first derivative of this is, well, quotient derivative of that, 1 over z plus 4, and then plus minus z plus 1 over z plus 4 minus 2. So this is z plus 4 minus z minus 1 over z plus 4 squared. Z's cancels. It's 3 over z plus 4. Second derivative, minus 3 over z plus 4 to the power of 2. So the integral over gamma, z plus 1 over z to the 4th plus 4z3 is going to be equal to this thing evaluated at 0 times 2 pi I. I have no idea what number, let's say 10. Probably not 10, it's probably like 3 or something, right? We can do the same thing again. Integral. This is another example. Sine 3z over z plus 1 minus 2i cubed to z. Gamma is going to be equal set of points z minus I equals 2. This is only going to cause problems at minus 1 minus 2i. Put in a minus I and check that. That is plus, there we go, minus 1 minus I equals square root 2, which is less than 2. So this is not analytic at that point. There's an isolated singularity there. And we can tell from the generalized Cauchy's theorem that this will involve the second derivative of the term above, evaluated at the point times 2 pi I, so we need the second derivative of this. So d dz sine 3z is going to be 3 cos 3z, and d dz of 3 cos 3z is minus 9 sine 3z. Oh, and I forgot a factor of 2 in the last. Sorry. Where was it? formula requires a 2 factor up there as well. So in this case, this is sine 3z over z plus 1 minus 2i3 dz, which is going to equal 2 pi I, 2 factorial, times minus 9 sine 3z and evaluated at minus 1 plus 2i. So this is minus 9 pi I sine minus 3 plus 6i, whatever that works out to be. Great, we can do things that look super complicated very easily. There's more examples. Page 103 in the notes. It's worth looking it up. And here we have section 4.7, which is some consequences of Cauchy's integral formula. So, sorry, I was watching a little bit of Counter-Strike. Okay, I've talked about most of these things already. The first corollary for Cauchy's integral formula is that if f is analytic inside and on a simple closed contour gamma, then f is infinitely differentiable inside and on gamma. That's not true for real numbers. For functions of the real numbers, as an example, f of x equal to the integral from 0 to x of the absolute value of t, which is equal to minus 1/2 x squared, when x is greater than or equal to 0, plus minus 1/2 x squared when x is less than 0. And this thing's not differentiable. It's differentiable once, but then it's not second differentiable at 0. So, second corollary. If f is analytic inside and on a simple closed contour, the values of f inside gamma are determined by the values of f on gamma alone. Another corollary. This is sometimes called Louisville's theorem. If f is analytic and bounded on C, then f is constant. And that's not true for the real numbers either. Infinitely differentiable, bounded, not constant. But if you're inside the complex numbers and you're analytic and bounded, then you are constant. A big difference, and it all boils down to the Cauchy-Riemann equations, because those are the equations which all these other theorems that you've seen follow from. proof of Liouville's theorem. F dash of A equals 1 over 2 pi I, the integral over gamma, Fz over z minus A squared dz. Gamma, a circle of radius r, and there exists some m positive so that the absolute value of f of z is less than m. And if you plug in the functions and you do the calculations as we did before, the modulus of f of a is 1 over 2 pi times the integral over gamma of m over z minus ra squared dz, and this is equal to 1 over 2 pi times the integral of m over the radius dz, is radius squared. That's going to be equal to 1 over 2 pi m over r. So as r goes to infinity, so as r can go to infinity, fz has to equal 0, and that implies f constant, which is pretty interesting. Well, last but not least, the fundamental theorem of algebra, for which I have promised you a proof a long, long time ago. Every polynomial of degree 1 or more has at least one root, one complex root. Proof: P of z equal to a0 plus a1z plus all the way up to an zn, n greater than or equal to 1, and a n not equal to 0. And we will assume that pz is not equal to 0 for all z inside the complex numbers. In other words, there is no root. Then f of z equal to 1 over pz is defined and analytic on z, because we can always take the derivative of rho. Now, in particular, the limit as z goes to infinity of f of z is equal to the limit as z goes to infinity, and with a little bit of rearranging, you get that this is z to the n over a n over z to the n plus a1 over z n minus 1 plus all the way down to a n, which is equal to 0 over a n, which is equal to 0. So I am out of ink. I'll be right back. Well, my apologies. I've been chatting away to myself for the last half hour without the video working, so now I have notes that are written up that I'm going to read out to you. But anyway, this is section 4.7. It's about consequences of the Cauchy integral formula, which is itself a consequence of the Cauchy-Riemann equations. So the first one is that f is analytic. If f is analytic inside and on a simple closed contour gamma, then f is infinitely differentiable inside and on gamma. I've spoken about that a lot. You've seen that, and I've tried to argue for that before in many other ways. And in particular, while it is a consequence of the Cauchy integral formula, a rather clear and nice direct one, we've already discussed why it holds due to the Cauchy-Riemann equations and the fact that Yeah. Anyway, and it's important to note this is not true for functions of real numbers. So this is a function from the real numbers to the real numbers whose first derivative exists everywhere, but whose second derivative does not. Another corollary, if f is analytic inside and on a simple closed contour, the value of f inside gamma is determined by the values of f on gamma alone. Yes, that's the Cauchy integral formula, really. Liouville's theorem, which is another corollary, if f is analytic and bounded on C, then it is constant, which I think is pretty interesting. That's not true for the real numbers either. This is a function which is analytic. It's differentiable everywhere. It's infinitely differentiable. It's not bounded. It is bounded, I mean, but it is not constant. So proof of Liouville's theorem. First we take Cauchy's integral theorem for the derivative. We take gamma, a circular radius r, and basically we show that that inside and on that circular radius r, the modulus of z has to be less than m, and that's essentially because f is continuous, and it must be continuous because it's differentiable. So the modulus of the derivative is less than or equal to this expression, and this thing here is of course r squared, and we're taking the integral over the curve gamma here. So when you do that, you pick up an extra factor of gamma that of r that cancels with this, so you get 1 over 2 pi mr. But r can go to infinity because f is analytic everywhere on the complex plane. So as r gets very, very big, this gets very, very small, and that means that the modulus of the first derivative has to equal 0, which means that the derivative has to equal 0, which means f is constant. And lastly, we have the fundamental theorem of algebra, which I have promised to prove for you, that I did promise to prove for you a long time ago. So now I can actually give you the proof. So the statement of the theorem is that every polynomial of degree 1 or more has at least one complex root. Here's our polynomial. Excuse me. That's me banging the web camera stand. Here's our polynomial, and we're going to assume that it's non-zero, so it has no root everywhere. Then f is 1 over our polynomial. And importantly, we assume that n is bigger than or equal to 1, and the first term is not equal to 0. So we take the inverse. This thing has to be defined and analytic everywhere on C, because that is non-zero. So we take the limit of f of z as z goes to infinity, that has to equal 0. So that means that there's some radius, so that for all z, modulus of z bigger than that, outside of the circle, the modulus of z is less than 1. But f is continuous on this circle, and we can even put a less than or equal to equal on there. That means there exists some real number, so that for all z inside and on this set, the modulus of z is less than r, but that implies that f is bounded and it's analytic on C. And by the previous theorem, that implies that it's constant, and that's a contradiction because we know that this is definitely not constant, because we have an explicit formula for it, and we can try two values. The fundamental theorem of algebra. There you go. No algebraic proof is known, and it goes through the Cauchy-Riemann equations. Very good.